Hey everyone, my name is Ben, and I'm going to be talking today with my co-host Pratyush about our experience scaling Flink in the real world. These are lessons we've learned over the last 5 years, operating Flink at an increasing scale at Stripe. We both work on the stream compute team. It's kind of a platform team that sits below a lot of the use cases and enables wide adoption of Flink at Stripe. Just to give a little context on the kinds of scale that we're talking about, we run over 1,000 different Flink jobs. These jobs solve a variety of use cases. We also serve 100+ unique applications. These applications sometimes run multiple jobs. So you could imagine different configurations of the same application. We enable users to use the entire data stream API. Almost all of our use cases use the data stream API, and it's pretty much unrestricted. In terms of volume of data, we process petabytes of data a day. There are a large number of use cases that engineers at Stripe use Flink to solve. Many of these take the form of money movement, fraud detection, change data capture, and most recently, usage-based billing. There are a few core requirements that our users have for Flink, and these are the main reasons why engineers pick Flink. The main ones are low latency, complete data processing, stateful processing, and some of our users use an incredible amount of Flink state, over 10 terabytes of Flink state, and high throughput. Another kind of unique requirement that I think comes from working at a financial company is that almost all of our use cases require state compatibility. So our users really expect that through changing their Flink application time and time again, that they'll be able to restore from their state. Now, one lesson that we've learned, and one lesson that a lot of our users have learned, is that operating Flink can be quite challenging. And there are a lot of challenges that come with meeting the requirements that our users have. So our large state applications take a long time to download state from S3. Low latency and state compatibility means that every time a user changes their Flink application, we need to make sure that that change is going to succeed. And if it doesn't succeed, or if that application starts failing in production, we need to be able to mitigate that issue really quickly. And that usually means mitigating the issue without committing a change in Git and deploying it. Same story for high throughput applications. High throughput applications experience a lot of scale-related incidents. This could be hotkeys, this could require horizontal scaling, et cetera. And then complete data processing requires really understanding the use case and consulting with users. In learning about, these operational challenges have informed how we actually operate and deploy Flink clusters at Stripe. So, for example, we operate one job per cluster. We always have isolated clusters per job and don't really do any multi-tenancy where multiple jobs will share a cluster. This kind of avoids, whole classes of noisy neighbor issues. We also run 2 job managers, so if one goes down, the other will pick up. We run an extra task manager, so if one goes down, the job can still get scheduled right away. Zookeeper high availability, kind of self-explanatory. RocksDB, everyone uses RocksDB. This is true whether you store a little state or whether you store 10 terabytes of state. And we encourage users to deploy their applications daily. This kind of avoids, certain issues around resource leaks. Despite these recommendations and this infrastructure, we still experience a lot of incidents at Stripe. And we took a step back and tried to understand how we can systematically drive down incidents to increase our scale, increase adoption, and overall decrease the amount of time that Stripe spends on KTLO and remediating incidents. So we took a step back and broadly categorized incidents in these 4 categories. And we kind of thought about them in terms of the complexity to resolve the incident versus how frequently we actually see this in production. And we're going to start from kind of like the right side and then move left. I'll be talking about the most frequent incidents, and then Pratyush will talk about the more complex ones. So, starting with change management. If you've used Flink before, you might know that upgrading an application is actually quite challenging. So, upgrading an application is a database migration. It's a complete job graph change. Users can make arbitrary changes. And we actually have really tight requirements around change management. And as your scale increases, as you run more jobs and more applications, the reliability of your change management solution needs to increase as well. And if it doesn't, you're actually going to increase, an order of magnitude. Each time you increase your number of applications, you're going to increase your number of failed deploys. Now, failed deployments might not be a big deal to you, but failed deployments consistently violate our users' SLOs, right? Every time there's a failed deployment and there's a job that isn't running at the end of that deployment, an engineer needs to get paged. That takes 15 minutes. An engineer needs to trigger a new deployment. That takes about 20 minutes. And suddenly the application's been down for 35 minutes. And their SLO might be 5 minutes, might be 200 milliseconds, depending on the use case. So challenges with the deployments. This is always kind of surprising, when people don't really know about Flink. They haven't seen Flink, haven't used it before. It could be hard. You have a job, you have some state, the cluster's up and running. Like, please just run the job, please. But you're very smart. You've used Flink before, and you know that a lot of different things can go wrong. Right, you might use a source that isn't authorized. You don't have the right access control. You might not have the right flags set. Your state might be incompatible, et cetera, et cetera. Now, I have a talk last year that tried to explain how to solve all of these issues. And it's interesting, but it's not what I would do if I could do it again. Instead, I would recommend that you invest in rollbacks. Rather than try to prevent every single issue, I think you'll actually see a lot more leverage out of trying to roll back to the old job instead of proactively trying to identify everything that could go wrong. So rollbacks solve for a variety of issues. They solve for issues that you might not even know exist yet. And, if you invest in a reliable rollback solution, then you can kind of figure out why the deployment went wrong at a very leisurely pace instead of in the context of an incident. We implement rollbacks by monitoring for checkpoints. So checkpoints at the platform level is a very consistent, uniform way of understanding application health. And then as soon as an application checkpoints, it's no longer eligible for rollbacks. This really simplifies the story around state management. You never have to use a checkpoint from a new job to submit an old job. This is pretty important when you start thinking about schema evolution, and that while schemas are evolvable in one way, they aren't always evolvable in the opposite way. So our control plane and our change management solution, we do this clever thing where we generate the job graph in a job graph service, and then we store it in a database. And this is really convenient because then we have a persistent reference to the job graph. It lets us use the same exact job description when we go to roll back the job. This is really important because at Stripe, users often use things like S3 or feature flags or dynamic configuration to produce their job. And that way, if that kind of configuration has changed since that job was deployed, we make sure that we're actually using the same job graph with the same state on the same cluster during the rollback. So if that new job fails on the new cluster, we can cancel it, retrieve the job from the database, and then submit it to the old cluster. And we know that that is going to succeed most of the time because it's literally the same cluster and the same job graph and the same checkpoint. Moving on. So that's change management. You'll find that change management is probably something you'll need to continually invest in over time. Scaling is somewhat similar. So if you operate at high throughput, I'm sure that you've seen a scale-related incident before. And there are two broad classifications of scale-related incidents that I think about. One requires horizontally scaling a job, and one requires vertically scaling the job. I'm not going to dig deep into scaling today because scaling is kind of intuitive. There's an autoscaler in the Kubernetes operator that I'd recommend you use. But I would definitely recommend thinking through how you respond to scaling incidents. Think about the time to remediate the scaling incidents, and then think about your users' SLOs, and make sure that you can actually respond to a scaling incident while meeting those SLOs. Usually, this means having some out-of-band way of either rescaling the job, increasing parallelism, and increasing the number of task managers in the deployment, or increasing the number of resources, that's CPU, memory, networking bandwidth, per task slot in your task manager. And being able to do this, without needing a git commit or anything like that. Without further ado, here's Pratyush to talk about latent issues.
Hello, I'm Pratyush. I'm also a software engineer at Stripe. So now we're going to talk about latent issues. So you have a running Flink job. It's been running for a couple of days. Nothing is going wrong. And suddenly, your app starts restarting. There's one restart, second restart, and it's persistently crash looping. In the way Flink runs, that we've noticed that if you have a single thread leak, it'll cause a job restart, which will cause a thread leak in another task manager, which will go down. Then you have a cascading failure. We see thread leaks. We see timer leaks, wherein your RocksDB state persistently is increasing with the number of keys you have. Then you have connection leaks, metaspace leaks, and the whole list of all failure modes that you can think of. This is a sample incident that we saw something last Tuesday, wherein we have a custom Kafka client. Let's ignore the Kafka client, wherein we were opening a metrics reporter. This metrics reporter was never closed. And we had this in production for about 3 years. And the Kafka API hadn't failed this way, wherein they were starting to time out, and we saw this thread leak and had to fix it. For these kind of cases, we generally don't have a single remediation, but it's more like always do slow phased rollouts. At Stripe, we consider availability tiers, which are generally dependent on the max allowable downtime, like deploy your changes to the lowest tier, moving on to more critical applications. Then we've been able to mitigate a whole lot of metaspace leaks just by using static class loading. This is, we have the liberty to use per cluster, like per job clusters, which means we don't deploy the jar during job submission. So we can actually embed it in the container and use static class loading. The third thing is we auto-remediate via synchronized restarts. Like whenever we see a leak, we want to re-trigger a deployment rather than letting the apps fail persistently. This prevents the cascading failure mode, wherein a leak in a task manager going down causes sequential failures until all task managers have restarted. Now we're going to talk about dependent outages. Flink at Stripe lies between the synchronous world and our data land. So which means we interact with everything that is a data store at Stripe, including all the RPC services. Our main sources are Kafka and Iceberg, and our main sinks are Iceberg Kafka, but we also do interact with gRPC services for event enrichment, etc. Our primary fault domains here is like Zookeeper. We use Zookeeper HA, and when you're running thousands of apps, you'll see some clusters having issues. Then, because of the usage of Kafka, we see Kafka publish availability a main concern. In the way the basic Kafka partition has single partition and unavailability will cause a job restart. And we want to be resistant to that. And then thirdly, upstream outages or even partial data incompleteness can cause your application to output the wrong data. Being a financial company, this is very disastrous. Like, we move real money according to what our Flink apps process. So we want to be sure that our data is always complete when we action on it. About Zookeeper, like, our main remediation is making our architecture resilient to Zookeeper failures. For example, we generally run Flink for more critical apps for one Flink cluster mapped to a single Zookeeper. And we don't run like multiple. The second case, we don't run our entire fleet on a single Zookeeper. Then, rather than that, when efficiencies are concerned, we'll share N-to-N relationship, wherein like a max of 10 Flink clusters will same a Flink Zookeeper cluster. This ensures that if a Flink application has concerns with correlated failures with other Flink applications, they don't go down at the same time. Like, for example, when one of the Zookeeper clusters goes down, like 5 of our Flink jobs will go down, but not all of them. And we are not provisioning like hundreds of Zookeeper clusters, which has like a significant amount of cost. The second thing we realize is like Flink, the Kafka producer API relies on a single Kafka broker availability because the retries are on the network level. We running like low latency application wherein downtime of greater than 5 seconds can cause customer impact. We want to avoid these failures. Like Flink, like Kafka at Stripe doesn't guarantee a single broker availability. There's no SLO for that. So what we end up doing is like we add a proxy layer, which helps us retry failures on a different Kafka cluster. Our sources and sinks are both aware that even you're interacting with multiple Kafka clusters at the same time. My colleagues from the stream infra team, then for our remediations, like we recommend like isolate key infrastructure, ensure that your failures don't have correlated Flink apps sharing the same infrastructure. Then sources and sinks should be highly available, like making sure Kafka S3 have high availability, and gRPC services have DLQs. Like if you have an async operator, make sure they interact with each other correctly. Our colleagues at the Kafka team did this talk where they explained how they run Kafka with 6 nines of availability. Basically the proxy layer we chatted about. Then there's this interesting failure mode about late arriving data, like because we don't rely on single Kafka cluster availability, a single partition could be down and your job may not realize it's down. Like generally we recommend users use add idleness, because otherwise it's difficult for most app owners to understand why my watermark isn't progressing. Like users just paste it on and don't realize that there's a trade-off here. So what Ben talked about, whenever we want complete data correctness, like if you're using an accounting job or you're safeguarding money, we want you to be sure that every architectural decision that you make in your FIMP application is correct. So don't use an idleness timeout. Make sure your watermarks only progress when you see data for the in the next timeout. That's it for me. We are hiring. If you wanted to join our team, feel free to go there. My team itself is hiring right now. Thanks. And we have about 9 minutes for questions. Yeah.
Hello. Yeah, thank you for the talk. So, as far as I understand, you're using a session cluster in a way typical for a standalone cluster. Is there any particular benefit for not using a standalone cluster?
Yes.
Standalone deployment mode, sorry.
Do you mean application mode?
Yes.
Yes.
Yeah.
So the question is, we kind of called out that we use session mode instead of application mode. Are there any benefits to using session mode? I would say the main benefits are that we get to coordinate a very low downtime deployment. So we're able to spin up a cluster, and we're able to generate a job graph. And then only when the new cluster is spun up and the job graph is generated do we cancel the old job, and then we can immediately submit the already generated job graph. Using application mode requires you to generate the job graph on the new cluster, and you do it at job submission time. And that means you have to cancel the job and then generate the job graph and submit the job. We have very little control over how long it takes to create a job graph. That's executing user code. And so it's surprisingly high leverage for us to actually reduce that minute or two. Some users take quite a long time.
Thank you.
Thank you both. You mentioned the automated rollbacks, and it also sounded like you're using the Kubernetes operator. Could you share a bit what it looks like from the developer's perspective in, can they control automated rollbacks, and also how will you actually, you've seen checkpoint failures, how do you actually initiate it from the, your program that's doing these deployments? Yes,
thank you. The question was, kind of around what is the user experience around automated rollbacks, and how do we coordinate them at sort of the technical level. So automated rollbacks, first off, we don't actually use the open source Kubernetes operator. There are some kind of arbitrary reasons why we don't, but we actually wrote our own control plane, and we deployed to multiple Kubernetes clusters. In terms of the user experience for configuring rollbacks, users can decide essentially a maximum amount of time before a rollback is initiated, and then the application needs to be submitted, state needs to be hydrated, and a checkpoint needs to be completed within that time. The reason we chose this strategy is to help users think about what is the maximum amount of downtime I might incur as a part of this deployment if it fails? And they can think about that effectively by adding, that timeout to the amount of time that it might take to roll back. In terms of actually coordinating the rollback, typically we already have the state handle, the checkpoint or save point that we use to submit the new job, and we're just calling cancel on the new job via the job manager.
Great, thank you.
All right, thanks for the talk. I was wondering what telemetry you guys had to classify the class of leak errors that you found, and how much like orchestrated restarts alleviated that problem?
For telemetry, like for thread leaks, thread count, for memory leaks, it's generally your GC time keeps on increasing. For one of the timer leaks I mentioned, have some, like we use RocksDB metrics to figure out the number of timers are growing or not. And yeah, and then the second question was, sorry,
Oh, how much like orchestrated restarts helped with those issues?
Yeah, so the second question is how much does orchestrated restarts help? So orchestrated restarts are generally our last defense. Like we don't want to reach that state. So I would recommend not doing those unless you can't solve for something. And they are helpful for like when you start seeing a new problem, but not really helpful once you see something recurring every few days. Then your on-call is a very bad experience. Your orchestration restarts fail in weird ways. So just use it for your unknown unknowns, not for known errors, is my recommendation.
Thank you for the talk. So you mentioned you have some jobs with very large state, like terabyte scale, and you also mentioned that you have jobs with low latency requirements. So I wonder, do you actually separate those two jobs into different classes, depending if you need low latency processing or what are the state storage needs, or do you have any standard techniques for minimizing checkpoint recovery time for reducing the latency introduced by the process?
Yeah, that's a good question. The question was essentially around large state, and do we separate use cases around large state or latency, like have users choose one or the other? And then for large state applications, do we have any like strategies for maintaining low latency? I don't think we have any like formal classification around large state or low latency, but in conversations, it often comes up, if we're gathering requirements for a new use case, we definitely ask about latency requirements and then try to estimate state size, though there are challenges to trying to estimate state size before an application is written. I guess we have some classification now in like slot types. We basically, users have to like pick how many resources they need per task slot, and one of those resources is disk space. So we could kind of infer it from the amount of disk space that is made available per task slot. In terms of low latency, I mean, we typically do checkpoint deploys, which means we don't have to like deseriate. We use checkpoint deploys and we use native incremental RocksDB checkpoints. So we're mostly network bound on restoring from checkpoints rather than CPU or deserialization bound. So that's like a little bit faster. And then vertically scaling task manager instance types to get more network I/O, but definitely haven't uniquely solved this problem.
Yeah, like in the end, it's some users just throw money at it. Like they'll just severely over provision, so you'll have way more network throughput. So your checkpoint rehydration would be fast enough, but like it's surely not the best outcome that we want to achieve in the long term.
Got it, thanks. Another short question, if I may, is I was curious why do you rely on Zookeeper for high availability rather than Kubernetes itself?
Can you say that one more?
So the question is, why do we use Zookeeper HA, not Kubernetes HA? So as Ben mentioned, we have some limitations on how we can access Kubernetes clusters. So it's a purely arbitrary reason, not something systemic.
Got it, thanks.
Yeah.
Hi. You mentioned that you're mostly relying on checkpoints. So how about upgrading Flink version? In this, do you have any special way of doing this? Taking save point, maybe in the background or something like that?
Yeah, the question was around Flink upgrades. We mentioned checkpoint deploys. Do we do anything special, like using a save point for a version upgrade? We do have some tooling around version upgrades and like thought about it. That being said, we do them every 2 years, and they take about a quarter for us. So we haven't. I think like the main motivator for us to get better at upgrades is if we wanted to stay really close to master. You know, if we wanted to do Flink upgrades every week or something, that would be like a really big motivator to get a lot better at upgrades. I've seen checkpoint deploys work for the most part for version upgrades.
Yeah.
For minor versions, you know, upgrading with a checkpoint usually works. Rollbacks will you know, roll you back to the old version if it doesn't work. And users can pick between checkpoints or save points, so we don't do anything really special.
Okay, thanks.
Right. Looks like we're out of time. Oh, or do we have to?
Yeah.
Okay, just one quick question. Since you have so much custom logic anyway for this automatic rollback, have you ever considered a way to get the new job deployed and running and create a checkpoint before you even cancel the previous one? And if yes, if you discard that decision, yeah, what were the challenges?
Oh yeah, I would like to do that. I think the main challenge is we'd have to get really good at educating users on how to implement that kind of deployment strategy and make sure their downstreams are safe and make sure that Kafka is adequately scaled for 2x the volume or proxies or gRPC clients. It turns into like a little bit of a bigger project. And especially if you're doing a lot of deployments in parallel, like if we could, in aggregate, 2x our throughput to Kafka, then we could actually cause like a pretty severe incident in Stripe. Yeah.
Yeah.
It's a good question. Yeah. Thank you, everyone. We'll hang out if you have more questions.